In section 6.1, we had functions of discrete random variables that were discrete random variables. In section 6.2, we had functions of continuous random variables that were continuous random variables. In this section, we have functions of continuous random variables that are sometimes discrete and sometimes mixed. And here we derive their PMFs or their PDFs depending on the circumstance. So let's start with a simple example. Suppose we have a random variable x and it has some arbitrary CDF. And now we let y be the output of a clipping circuit. And the way this circuit works is that the output is 1 if x is less than or equal to 0, and it's 3 if x is greater than 0. A circuit like this is sometimes called a hard limiter. And now what we want to do is we want to figure out what is the CDF and the PDF of y in terms of the CDF and PDF of x. So this is actually a pretty simple situation because even if x is continuous, the output g of x, the output of the limiter, is discrete. It's either 1 or it's 3. And the probability that y is 1 is equal to the probability that g of x is equal to 1, and that's equal to the probability that x is less than or equal to 0, and that, of course, is the CDF of x at 0. And the only other possibility is that y is 3, and so the probability y is 3 is 1 minus the CDF of x at 0. So we found the PMF of y, and we can express this in terms of a CDF in the way that we learned several weeks ago. So here is y, here is the CDF, and here's 1, here's 3, and this function at 1, it makes a jump. The height of the jump is the value of the PMF at that value, so that is fx of 0, and it's flat, then it jumps to 1. And the corresponding PDF of y is just the pair of impulses. And we could just as well here is at 3. And that's the complete answer to this problem. The answer in the textbook is in this slide and the following slide. And it's essentially the same answer, although with a few more words and a little more detail. So the last problem was easy, so let's do a slightly tougher problem. In this problem, the output voltage of a microphone is a Gaussian random variable V, and the expected value of this is 0, and standard deviation is 5 volts. And the signal is the input to a soft limiter whose output is W. And the definition of this soft limiter is that for V less than minus 10, the output is minus 10. And then there's a linear region where W is exactly equal to V. And then there's a saturation when V is bigger than 10, W maxes out at 10. And what we'd like to find are the CDF and PDF of W. So this problem, you should be able to see that the output W is going to be a mixed random variable. If V is bigger than 10, then W is going to be 10. And the probability W is 10 is going to be some non-zero value. Similarly, all v's less than minus 10 produce w equals minus 10, and the probability of that is also non-zero. But in the region in between, where w is between minus 10 and 10, it's going to look like identical to v. V is continuous and Gaussian, and so we ought to see a PDF of w in this region that resembles the PDF of v. So let's handle the easy cases first. In the easy cases, we know that the probability that w is equal to 10 is the probability v is greater than 10, and v is Gaussian and zero mean. So this is the probability v minus 0 over sigma v, which is 5, is greater than or equal to 10 minus 0 over 5. Of course, the 0 is mu v, the expected value. And so this is equal to q of 2. And similarly, the probability w is equal to minus 10 is the probability v is less than or equal to minus 10. And this is equal to the probability v over 5 is less than or equal to minus 10 over 5. And in fact, this is phi of minus 2, but phi of minus 2 is also equal to q of 2. So what's left is to find the CDF of w in the region where w is between minus 10 and 10. In this case, we go back to the graphical method we introduced before, and we think about, we mark a point w on the w-axis, and we're interested in finding the probability that the w we observe is along the purple stripe, all values of w less. And now we translate that into finding a VW pair below the threshold line W. As a VW pair, what we're doing is finding all the VW pairs along this segment. And the final step is to observe that this point corresponds to V equal to W, since it's derived from the 45-degree line where W equals V. And we're translating the probability of the VW pair along this line into the probability that that V is along this green segment that goes back to minus infinity. In short, for W's between minus 10 and 10, the CDF of W equal to the probability W is less than or equal to W is equal to the probability V is less than or equal to W. It's equal to the CDF of V at W. And of course, since V is Gaussian with mean 0 and standard deviation sigma V equal to 5, this is just equal to phi of W over 5. And now, keeping in mind that W is bounded between minus 10 and 10, we can just simply write down the expression for the CDF of W. We've acquired all of the facts we need. So this is 0 for W less than minus 10. It's equal to Q of 2, we found out earlier, at W equals 10. It's equal to phi of W over 5 for W strictly between minus 10 and 10. and it's equal to 1 for w greater than or equal to 10. And then we keep in mind that at w equals minus 10, this lower limit this limit is phi of minus 10 over 5, phi of minus 2. But phi of minus 2 is the same thing as q of 2. And so we can simply combine these two statements as this CDF is 0 for w less than minus 10. It's equal to phi of w over 5 for minus 10 less than or equal to w less than 10. And it's equal to 1 for w greater than or equal to 10. And now we found the CDF, which we were asked for here, but we still have to find the PDF, but we better use another slide because we've run out of room here. So we found on the previous slide that the CDF of W is equal to 0 for W less than minus 10. It's equal to phi of W over 5 for minus 10 less than or equal to W less than 10. It's equal to 1 for W greater than or equal to 10. And if we plot this function, we have minus 10 and 10. And this function is equal to 0 up to minus 10. But then it has a jump. And the height of this jump is exactly equal to the value of phi of minus 2, which is equal to q of 2. And now this function looks like the Gaussian CDF phi of w over 5. It's just the usual sigmoidal S-shaped curve. And then finally, it has one more jump at 10. And the height of this jump is also equal to q of 2. And that's the complete CDF of W. And now to find the PDF, you simply take a derivative of this function, and you can do this piecewise. And these two terms, the derivative is 0, but we have to keep track of the fact that there's the jump discontinuity at minus 10 and at 10. So when taking the derivative, we get we get 0 for w less than minus 10. We get q of 2 times delta of 0 at w equals minus 10. We get the derivative of phi of w over 5. And so let's just make a little note here. For w between minus 10 less than equal to w less than 10, we have a CDF, which is phi of w over 5. So this is a Gaussian CDF corresponding to mu of w equal to 0 and sigma w equal to 5. So rather than try to write out the integral expression for the phi function, we just know that this derivative is the Gaussian PDF with the same expected value and the same standard deviation. And so this is equal to 1 over square root 2 pi 5 squared e to the minus w squared over 2 times 5 squared. So this is technically 1 over square root 50 pi e to the minus w squared over 50. And finally, so we have that expression goes here, 1 over square root 50 pi e to the minus w squared over 50 for minus 10 less than strictly greater than w, less than 10. And then we have the next jump discontinuity in the CDF here at w equals 10. So we have another impulse. So, and the height of this is q of 2, delta of 0 at w equals 10. And then we have for w greater than 10, the derivative is again 0. So all of this is kind of a mess in terms of algebra, but it's pretty simple when you look at it as a PDF. As a PDF, we have an impulse at minus 10, and the weight of that impulse is q of 2, or phi of negative 2, if you prefer. We have another impulse at of weight q of 2 at 10, and in between the two, we have a nice symmetric, although my drawing doesn't show it, Gaussian PDF, right, corresponding to standard deviation 5 and and expected value 0. So this is our PDF. My drawing could be better for sure, but I think the answer's right. So these slides from the textbook essentially repeat what we did. Uh, Once again, this graphical method of saying, oh, it's W less than W corresponds to V less than W because of the VW pairs being along this line. We use that again. Here, the graphical method was kind of used for the cases also W less than 10, like W's down here had 0 probability because the VW pairs are along this function curve. And then for W's greater than or equal to 10, it means the VW pairs, all of them were included because every VW pair that's possible has W less than or equal to 10. You can check that the CDF here is exactly what we derived on the earlier slide. So this quiz tests all of the basic ideas using a pretty simple kind of a ramp PDF and a one-sided limiter. If you can handle this quiz, then you're probably pretty good at these problems. It helps to start by plotting the PDF of x. Starts at 1, down to 0 here at 2. And of course, the area under the curve is exactly 1 as usual. And it's also helpful to plot the function y as a function of x, and this function is it's kind of a one-sided limiter, maxes out at 1, and so it saturates for all x's at 1 for all x's greater than 1. For part A, we first identify where the CDF is obviously 0 or 1. So in particular, the probability x is less than or equal to 0 is 0. And so the CDF of x at 0 is 0. And the probability x is less than or equal to 2 equals 1. And so the CDF of x equals 1 for x greater than or equal to 2. And for x is in between 0 and 2, we simply solve the CDF of x is the integral of the PDF 0 to x fx of u du, and algebraically this is the integral 0 to x 1 minus u over 2 du, and this gives us u minus u squared over 4 from 0 to x, and that's x minus x squared over 4. So putting these pieces together, we have part A. The CDF is 0 for x less than or equal to 0. It's equal to x minus x squared over 4 for x between 0 and less than 2. And it's equal to 1 for x greater than or equal to 2. And if we wanted to plot this, it would look like here's 2, and the function is 0, and it goes up like a quadratic, something like that. And then it flattens out and is simply equal to 1. For the rest of this problem, it's helpful to copy over the PDF, the function y as a function of x, and the CDF of x. And now proceeding, we'll do step B. We're asked what's the probability y equals 1. And we see from this function of x that y equals 1 if x is greater than or equal to 1. So this is the probability x is greater than or equal to 1. And that's equal to 1 minus the CDF of x at 1. And this is precisely 1 minus 1 quarter is equal to 1/4. The reason part B asked us to find this is simply to point out that y takes on the value 1 with non-zero probability because it kind of clues us in that y is a mixed random variable. Now to find the CDF of y, we observe that we're going to see, because x is between 0 and 2, we're going to see x-y pairs that are along this segment that I've highlighted in the pinkish reddish color. And that's because x is between 0 and 2, and these are the corresponding values of y. So from this, we observe that for y greater than or equal to 1, the CDF of y is equal to 1 because y is always less than or equal to 1. Now, for the more difficult case, we think about y's between 0 and 1. And that corresponds to drawing an axis, a threshold here, y, and then asking what's the probability that our y is below that threshold. And this corresponds to y being on this segment, and that corresponds to x being on this segment. So if in fact along this along this segment, y equals x, so this point here is x equal to y. This intersection point is the point y comma y, x equals y and y equals little y. And what we see is that because the xy pairs lie along the line x equals y, the CDF of y in this interval, the probability y is less than or equal to y, is simply the probability x is less than or equal to that same value of y. So to be clear, the event y is less than or equal to y corresponds to y's along in this region, and that corresponds to x's in this region. And now, to finish this problem, we know that this is the CDF of x at y, and this is y minus y squared over 4. Keep in mind that this is for y's greater than 0 and strictly less than 1. Finally, for values of y less than 0, we keep in mind that the fact that x is between 0 and 2, it's always in this interval, implies that y is always greater than or equal to 0. And it then follows that the CDF of y is equal to 0 for y less than 0. So putting these pieces together, we have the CDF of y, and it starts at 0, and then it goes up quadratically up to 1 because of this function. And at 1, this function is equal to 3/4. So we'll mark that as 3/4. But also at 1, the CDF exactly 1, it jumps up to 1. So there's this jump discontinuity. It just bumps straight up like that, and then it's flat. Algebraically, we can write CDF of y is equal to 0 for y less than 0, y minus y squared over 4 for 0 less than or equal to y and less than 1, and 1 for y greater than or equal to 1. Now, to find the final step is to find the PDF of y, and we do that just by taking a derivative. And of course, each piecewise segment of the CDF of y, we can take the derivative for each piece. But we have to remember that we're going to have an impulse because of this jump. So going piecewise, we have this is 0, and then it's going to be 1 minus y over 2 up to 1. And then at at 1, we're going to have an impulse, which has weight 1/4. So algebraically, we have this is 1 minus, we're taking the derivative of this function here, 1 minus y over 2 for 0 less than or equal to y strictly less than 1. Then we have 1/4 of a delta function, which I can write as delta of y minus 1 at y equals 1. And then we have 0 otherwise. And that's the PDF of y. There are a few more slides in this presentation. Those slides just repeat this solution, typeset nicely. I'll leave them in, so the PDF version of this presentation will have this solution all neatly organized.